everyone. I am here with Jonathan Le Roux. Jonathan is a senior principal research scientist at Mitsubishi Electric Research Laboratories, or MERL. Jonathan, welcome to the TWiML AI podcast.
Hi, thanks for having me.
So, we'll be digging into your work in the speech and audio field broadly. And to get us queued up, I'd love to have you share a little bit about your background and how you came to work on applying ML to those problems.
Sure, yeah. So my background actually started in mathematics. I studied math, pure maths for a while until my master's, and then did a master's with Cedric Villani, who later got the Fields Medal, and I was supposed to do my PhD with him, and like, but I wanted to do a gap year in China, so I ended up because I started studying Chinese and I like languages. So after spending a year in China and I got back, he said, "I'm going to Stanford. You might as well spend another year somewhere else." So I decided to go to Japan because I made friends there in China, Japanese friends there, and I started studying Japanese, and then I realized that maybe pure math wasn't actually so much my thing, and I looked around at what I could do, and I thought that math and languages kind of mix well. And I also I was really into music, and I started playing with in a band with friends, and I thought like kind of the intersection of all these interests was the speech and audio field, and I got introduced to a professor at University of Tokyo who was in there, and so I was able to do my PhD with him and with another professor in Paris. So that's kind of how I got into the field of speech and audio, and I'm really happy I did.
That's awesome. That's awesome. And a lot of your work is focused on this classical problem in the field called the cocktail party problem. Can you tell us a little bit about the background of that problem and some of the ways that you've kind of built your research program around it?
Sure. So yeah, I worked. The core of my work is centered around source separation, audio source separation, and in the field, the kind of the holy grail is the so-called cocktail party problem, which was kind of stated in that with that name by Cherry in 1953. And it's kind of if you imagine yourself in a cocktail party, and we humans have this amazing ability that we're able to entertain a conversation and kind of to focus on pretty much any given source of sound that we really want to focus on. And despite all the background noises and the reverberation and all these interferences that are happening in this very cluttered acoustic scene. And so what we've been interested in my group over the years has been to kind of to tackle this problem, to chop at it, and so first by working on speech enhancement, which is the separation of speech from noise, and then later on we worked on speech separation, which is separation of speech from speech, and this was kind of a big milestone because speech and noise have very different characteristics, and so you can kind of use this at your advantage to separate them from each other. You can use machine learning to learn these characteristics and then kind of classify one from the other. When it comes to speech from speech, then it wasn't clear really how you would handle this. Because they have by definition the same kind of characteristics. So we like the main challenge was how to deal with that problem, and so that's kind of where we started developing methods to do this efficiently using deep learning.
Nice. And is the ability to separate speech from noise or speech, is that a necessary prerequisite for a machine to be able to attend to a particular speech signal? Strikes me that we don't necessarily separate, we attend to.
It's a good question. I mean, it's actually a very good question whether we humans actually effectively separate in the
Hmm.
brain or not. And I think there is some hints that we are actually to some extent separating the signals.
Okay.
And maybe we're not separating all the signals. It's more like an attention mechanism where, like the higher parts of the brain kind of guide the lower parts of the brain to decide which features, which parts of the sound to focus on and to cancel other ones. So we're not completely separating a scene as a machine maybe potentially could do. But there is some hints that in neuroscience that's like uh, kind of part of a process. It's not necessary. You're right. Like you could totally design a speech recognition, automatic speech recognition algorithm that does not explicitly separate before recognizing noisy speech or even multi-speaker speech. And that's actually something that we did do, and we're not the only ones. So we uh, basically even nowadays, I would say the state of the art in um, like kind of single channel noisy speech recognition does not necessarily involve enhancement. It's sometimes surprisingly, even though it sounds much better, uh, it's often a better strategy to just include more noise in your training data and to let the neural network that does the transcription be robust to noise inherently by virtue of training, instead of like thinking that you're doing the network a favor by removing the noise when you're actually probably introducing some artifacts that are bothering the system. So it's not always the best strategy, but it. I mean, going forward, I think as the enhancement algorithms get better and better, it's likely that it will become probably the state of the art to include some form of enhancement.
Got it. Got it. Maybe a good way to talk through your work in the field is to start with a recent paper, and as you kind of describe what you're doing there, you can talk through some of the work that's led up to it. And so that recent paper is a new formulation of the cocktail party problem that you call the cocktail fork problem. What does that mean?
Yeah, so that's we try to be a little bit cute there, and so basically, this project started with myself not being an English native speaker and trying to listen to movies and not always being able to catch a dialogue with all the special effects and the music, and I was like, man, I really like to be able to just separate the dialogue and enhance it. And some smart TVs, claim they can do this, and they can do to some extent, but they mostly rely on some form of equalization. They don't actually separate the sources. And so we thought, well, we have all these separation technology that can separate speech from speech, and nowadays we also can separate, multiple types of sounds from each other, like for like a car from a from a bell, for example. And it was kind of a natural thing to try to see, well, how can we just formulate this problem as to separating a complex acoustic scene into like speech, music, and sound effects or sound events. And that's basically what we did. Like we like carefully crafted a data set that uses these three types of sources and tried to replicate with as much realism as we could the mixing process of like real soundtracks, like movie or TV show soundtracks. So in terms of loudness or in terms of amount of overlap, and to build a training set basically. And then we trained our kind of somewhat standard algorithms uh, for separation, and we tweak them a little bit in order to account for the specificity of the task. So that we called it the cocktail fork problem because there's three outputs, and cocktail forks happen to have three outputs, three branches. So I thought it was a nice hint at the cocktail party problem to call it the cocktail fork problem, because it's kind of it's a tiny easy version of the cocktail party problem.
Hmm. Hmm. And so y- y- given that you started with a um, kind of an inorganic training set, you created your training set from its component pieces, thus bypassing one of the might otherwise be the hardest part of training a model here. I imagine that the on the back end, the generalization was a big challenge in building the model.
It turned out that it actually generalizes pretty well. So we the demos that we put online were trained on only on this synthetic data set, and we show examples that we got just from taking YouTube videos, like movie trailers or TV shows, and applying the network pretty much as exactly as it was. Um, and it does make mistakes, but it does generalize pretty well. And actually, an interesting thing is at first we trained the network at 16 kilohertz sampling rate, so we downsampled the signal, because it was lighter weight, easier, I mean, faster to train and to try things. Interestingly, we first used a wrong version of the speech data set that was downsampled with a slightly too harsh band pass filter, like low pass filter, and it was leaving out a bit of frequency of the higher frequencies of speech. And when we applied it to these real videos, there was a lot of bleed from the speech, the high frequencies of speech. There is very squeaky speech in the other sources, like, and we're like, what is going on? And actually we realized that actually the version of the speech data we had was not full band, and when we retrained our models on a better quality data, that it just went away. So kind of interesting that, like, if you listen to it, you wouldn't notice, but the network definitely was not able to learn how to separate the high frequencies for speech.
Oh wow. It did the model um is the model language agnostic?
So we only train it on English, but we found that these speech separation models are pretty language agnostic. A few years back in 2017, we did a demo of speech separation, and that was trained on 30 hours of English, Wall Street Journal read sentences speech, and this was a live demo in Japan, and we were separating, English from Japanese and Japanese from French, or people who visited the demo tried every crazy combination, and it worked pretty well. I mean, it's not picking up on the language content; it's really the acoustics.
And when it's separating, how clean is the separation of the language? If you listen to the separated language, do you hear artifacts of whatever might be going on in the background, or
So it depends how you trained. Yeah, back then we only used clean speech for training, and actually, it is still a challenge in the field to extend these methods to work well on noisy, and especially in reverberant conditions. So like the data set that we put out in 2016, when we first came up with this method called deep clustering, that kind of revived the field of speech separation. It was the first one that used deep learning in a way that it could separate unknown speakers. You didn't have to train on a specific pair of speaker. It could be anybody. And we created a data set to do this based on the Wall Street Journal, and this is still used to this day, but it's kind of completely beaten out. Like the performance on that clean data set has become so amazing that it's pointless. It's like super clean, over 20 dB, so there's no. I think we solved that task. Not we, but the field, the community has solved that task. And the challenge now is to moving to more challenging scenarios with noise and especially with reverberation. So we put out a couple data sets to encourage the community to move on to that. We call them WAM, the Wall Street Journal WSJ hipster ambient mixtures. So and like the band Wham. Um, and it's People are now using this data set as well to try the algorithm in a more challenging scenario. The performance is of course much worse in reverberant and noisy conditions.
and when you say reverberant and noisy, you're talking about when the speech training data has noise associated.
Both the training and the test. So
Okay.
typically, like, if you don't train on data that has noise and reverberation, that will completely fail. But even if you include noise and reverberation in your training data, the performance is clearly not as good as in clean conditions, because the noise, but especially the reverberation, really smears the characteristics of the speech. Everything that is normally in a spectrogram, so in a time frequency representation of your signal, where you show the energy at each time and frequency, speech is very, very clean. You can see the patterns, but as soon as you introduce reverberation, everything gets smeared, and so it becomes much harder to first to um, for the network to identify the structure, then there's more overlap between because everything gets like mushed, so there's more overlap between the different sound sources. So you imagine, like, if let's say imagine like on a spectrogram, typically you have stripes when you have harmonic speech tends to be there's a lot of harmonic parts in speech, and these show up as stripes on a spectrogram. So if you imagine stripes and you have two sets of stripes, if they're very clean, you can probably uh, identify them and then make a mask that cancels one of them and only keeps one. But if both stripes are kind of smeared like and become like kind of mushed, then there's a lot of portions that overlap, and it's also harder to see the stripes in the first place. So it makes it difficult both to identify structure and also there actually is more overlap between the structures.
So when you so the way you've set up the cocktail fork problem, and maybe this is general to my question is general to other cocktail party problem applications. You've got speech and you've got uh other background things. It could be other speech, or it could be other the movie soundtrack and sound effects and the like. And then you pass it through this model and you have a speech stream that comes out on the other end. And I guess independent of whether you are working with clean speech or noisy speech on the back end, I'm curious how clean the output speech is. Or um, I'm trying to. I have a picture in my head of something that is doing. Uh, I I don't even know how to describe it. Like you some other application that's similar to this kind of separation, but I don't remember where it's from. But like you get the speech, but there's also kind of this warbling noise in the background that.
There's a in like kind of more conventional, I would say, separation methods. There's these artifacts that's kind of like that are kind of added to the speech. That's something that's typical of deep learning based methods. We don't observe that much actually. Um, Interestingly, yes, there's still artifacts. I mean, but they don't sound musical noise is not such an issue in deep learning based methods, and I'm not sure I have a good insight for why. Um, but yeah, it's sort of like these methods like introduce sort of a spread out noise across the spectrum that doesn't really have a structure, but then that kind of creates that kind of musical noise. I would say the artifacts in deep learning based methods are, I mean, most of the time it's really failure to separate, like, or you get when you're doing speech separation, an error that we very often get is that the speaker, if you listen to each, like you have two speakers and you separate them, the speakers are actually separated at any time instant. They're pretty well separated, but halfway through, the algorithm makes a mistake in how it stitched thing, and then it switches the speakers. And so if you listen with headphones, you're like suddenly like the speakers just switch sides. They're separated, and that can happen multiple times. So it's this kind of speaker permutation problem is a one of the issues that we have, typical issues that these systems have. And so people have tried to come up with methods to to alleviate that. Um, but yeah, that's and there's still um, a lot of artifacts. It tends to work pretty well, except when it completely fails. It's a that's a pretty typical thing in deep learning, I would say.
And you've talked a little bit about the spectrograph representation of speech. Do these models, yeah, tend to work like in the frequency domain or time domain, or like how do you think about the way they're working?
So there are multiple approaches in speech separation. Some historically, a lot of them were based in the time frequency domain. So what we do is we take short snippets of signals we call frames, and so we just put a window on a little bit of signal, and do a Fourier transform to analyze the frequency content of that small window, and so that gives us a vector, and then we have a bunch of these vectors, and this is what makes the spectrogram. And historically, people only mostly treated these numbers are all complex numbers. By the way, the Fourier transform gives you a complex number at each time frequency. Um, and Historically, people have looked mainly at the magnitude, at the length of that vector. of that complex number and the phase part, so the angle of the complex number, was kind of left as is because it was thought to be pretty difficult to model. And if you look at a picture of a magnitude spectrogram, so where you don't consider the phase looks very random, but the magnitude looks very nice with these stripes that I was mentioning. So it feels like you can do something about it. You can do machine learning on it. And that's what people have been doing. And still to this day, there's a lot of methods that only handle the magnitude part with, like, for example, with some transform, like a frequency transform, like what we call MERL transform, to gather some frequencies according to some filters. And that's what is used in speech recognition, for example. So we started with that, and for many years, most of the methods were based in the time frequency domain. Nowadays, the state-of-the-art methods either now include the phase, they include both, they model the full complex number in the time frequency domain, or they do not explicitly use a time frequency transform. They go straight from the waveform, the time domain signal, to the desired time domain signal. Implicitly, they're kind of learning the time frequency transform. So instead of using the usual Fourier transform, they use a filter bank, a bank of filters, and they let the network figure out what these filters should be. So it's very similar, and it's implicitly still based in some form of time frequency representation, but it's fully learned. So we see both types of methods.
Can you talk a little bit about the model and architecture that you used in the cocktail fork problem?
Sure. So that model actually we took from a kind of state of the art model for music separation called Cross and Mix. It was introduced by Sony, and what it's based on a recurrent neural network, bidirectional long short term RNN, so BLSTM. Its characteristic, what kind of makes it a bit different, is that in their model, you start from the mixture, and then you have multiple branches that have different transforms, different layers that go through that transform the signal in ways that the network can decide, and then they average this transform, and this goes through some BLSTM layers, and then they average again the outputs, and it's kind of this averaging that's between various branches that is the special sauce. And so we took this, and the only thing that we changed is that we thought that in the case of a cocktail fork problem, the signals that we deal with are so speech, sound effects, and music, and they have kind of different dynamics. Like some very, especially with sound effects, you may have very short impulsive sounds like bangs or claps, or you may have like long harmonic sounds like sirens, for example, and kind of the way you do your time frequency transform kind of dictates what characteristics of the signal you can focus on. So if you have a very impulsive sound, you want a very short window in order to be able to really analyze the frequency content of that very short impulsive sound. If you have a long sinusoid, you want a longer window in order to get a more fine-grained, like to narrow down the exact frequency. Otherwise, it's going to be more like a blurry representation. So the longer the window, the more fine-grained frequency resolution you get, but the worse time resolution you get. Everything gets more blurred in the time direction, and vice versa. So depending on the characteristic of signal, your choice of window length is going to impact what you can see in the signal. So what we decided to do is that we already had several branches in the Sony cross and mix algorithm, and we decided to specialize each branch to have a different window length, so to make it able to focus on different characteristics, to kind of nudge it to focus on different characteristics of the signal. So that was the main twist on that architecture that we had, and it did bring a small but significant improvement on performance.
And so, does that window length end up being a hyperparameter that you have to tune for each of your sources?
So yes, in the sense that we manually tried various combinations and looked at
Okay,
which one performed the best on a development set. Yes, we yeah we just tried some variety within a like a reasonable set of parameters. There's not many things to try.
got it, got it. You kind of characterize this as like a toy problem or a subset of the cocktail party problem. Going back to the broader pop problem. Yeah, how do you characterize where we are with regard to solving that problem with machine learning or deep learning, and what are some of the big uh, research directions and challenges that folks are working on?
Yeah, I would say it's a smaller version, but it's nonetheless it's pretty. I would say it's an important application. That it's kind of surprising to me that nobody actually looked at this earlier, because it sounds like it should be useful for analyzing YouTube videos, for example. If you want to know what's going on in a YouTube video, and maybe sometimes somebody's speaking, but you really want to listen more to the sound events, then you would like to separate the speech from the sound events. And sometimes you have music in the background that you don't care about. So it's we think of it as an important pre-processing step that we plan to use ourselves in our projects for this kind of multimodal content analysis. And to answer your question, I think the field is progressing very fast in the capacity that we have to separate general scenes. I'm very excited about the progress that's been made, and there's um, a lot of work that's been done on general sound separation and sound events. I feel like what is maybe what the challenges are the first the realism of data, like how realistic can you get can you make your data, and because it's still very important currently for these algorithms to train in a supervised manner, and we're only starting seeing methods that can be trained without supervised data. So what I mean by this is the typical way to train these methods is to get a bunch of sounds, mix them together, and this is your input, and then you ask the algorithm to come up with the isolated sources, which you already have because you mix them together. So that's easy. The downside of that is that that mixture may not be very realistic. So we made some efforts to do it, but it's never going to be the real thing. And so recently, some groups have developed unsupervised methods where you only have the mixture, and you can't ask the algorithm to be as close as possible to the isolated source because they don't exist. You don't have them. And so one of the methods, for example, was developed by my former colleague, John Hershey, and his colleagues at Google, and Scott Wisdom, um, is called Mix It. So what they do is they take two mixtures and they mix them together. And so they have the original mixtures, and what they have the algorithm do is very very simple, very clever. Is they ask the algorithm to to separate all the sources in this mixture of mixture, and you have many sources, and then they judge how well this happened by picking the best combination that comes back to each of the mixtures. And because the algorithm doesn't know which sources mix with each other, it has to separate all of them in order to be able to reconstruct the mixtures. So that's very simple. It works pretty well. Um, so I think these kind of methods and another work that we also did called weakly supervised source separation, where we trained a system where the reference signal, the only labeling we had was whether a, a type of a sound of a particular type was present or not in the mixture. So imagine that you want to separate dogs from cats, from bells from cars. and your data is mixtures of these sound classes, and in each mixture, which sources are present. Like, is there a dog? Yes, maybe somewhere there's a, you tell, yes, somewhere there's a dog, and somewhere there's a car, but that's it. That's all you know. And so we devised an algorithm to train the separation under that constraint. And the idea is that you have a separator come up with separated sources, and then you use a classifier that looks at each source and should tell you there's a dog in there when there should be a dog, and if it detects a cat, then you did something wrong. Um, so that's kind of one of those methods that try to reduce the amount of labeling that is needed to train these methods, and that's very important because if you go in the field and you record something, you may be able to ask someone to tell you which sources are present, but it's impossible to get the actual real isolated sources. Um, so these methods that kind of reduce the amount of labeling that's needed to train separation systems are pretty important going forward. Um, and I would say maybe yeah, I was going to suggest another challenge uh, of in the separation
Before we
field.
move on to
Yeah.
the next challenge, are there methods that uh, that approach it from weak supervision from the perspective of, hey, I've got a set of training data that is, it's speech in isolation. I know it's speech in isolation. I have sound effects,
Mm-hmm.
to put in the context of this cocktail fork problem. Sound effects in isolation, music in isolation,
Mm-hmm. Mm-hmm.
but not providing the mixture.
Yeah,
How
that's a good
far have you
question.
gotten with that?
Well, yeah, I think there are such methods like based on like autoencoders, for example. There are methods that try to do that. Uh, Now the question is like, if you have these sounds, why not mix them? So that's maybe one of the downside of this. But yeah, I mean, like in a sense, if you're able to train autoencoders on each source type, then it's pretty modular. Like if you have a speech autoencoder, for example, so this network is only able to reconstruct speech, and then you have a music autoencoder, then you can combine them to kind of separate speech from music. And So the RVS methods typically they don't work as well as the best the other types of methods that are not based on like generating
Yeah.
the
I
output.
think your implicit response is that a bad mixture is going to be better than no mixture at all.
I mean, I'm pretty sure that yeah, the autoencoders are going to go further, but at this point, yes, they don't work as well as this kind of more uh, training based on mixtures. Um, of sound. Yeah, that's and there's another type of scenario that is interesting is if you actually have um, example of speech and noise, and you have so I'm trying to remember the exact scenario. So you have example of speech and noise, and you have example of speech, but you don't have example of noise in isolation. Then you can still kind of do some tricks to train methods to separate the speech from the noise. So you have a mixture of speech and noise, but you don't have the corresponding isolated ground truth. But you also know what speech sound like, so you can then come up with some tricks to use these data to train a method, a separation system.
So you were about to mention the next or another
Yeah,
challenge in the
I mean
field.
something that is kind of that I'm excited about that we started a little bit working on still, and we need to go further. I think is this idea of hierarchy in sounds. So we published one paper on hierarchical source separation, where we tried to argue that source separation sometimes is actually a bit of an ill-posed problem. Um, because let's say you're in a bar and you're talking with people, and there's a band playing in the background, and you say, well, okay, separate that scene. What does it exactly mean? Like uh, if you're saying, if your problem is specified as separate speech from noise, that's pretty well posed, or speech from speech, that's pretty well posed. But as soon as you get into more complex scenarios, uh, you ask to separate the scene. Do you want to put all the people talking together in one group? Do you want to put the band as one coherent source, or do you want each instrument in the band? You want each person separately? So there's kind of a hierarchical structure of the sound uh, within a scene, and this hasn't been
I could even envision trying to impose some kind of spatial hierarchy, like the people that may be talking to one another because they're closer than more distant people.
exactly, yeah, that's another type of hierarchy. Exactly. So there's many different cues that we can use when we're in that scene to kind of make sense of it. But this hasn't been. I mean, the spatial information have been used in microphone array methods, but maybe not exactly in that with that angle, if I may say so. And so we tried to argue in that paper that like people should try to think about source separation as a hierarchical with a hierarchical angle. And the first thing that we did in that on that topic was to consider music source separation with a hierarchy of instruments. And so a slightly different idea of hierarchy, but basically we were saying that um, if a user um, wants to query a system to separate a particular instrument in a music mixture, and you allow the user to give you an example of what they want, and so they give you a sound snippet of what they want. And so let's say you have a rock band and they give you an acoustic guitar snippet. What do they mean? Do they want the acoustic guitar in that recording, if there is one, or nothing else? Do they want any guitar, electric, acoustic? Do they want any instrument that is kind of harmonic? So it's not exactly clear what they mean. So or so we thought, well, why not consider that hierarchy? Like, so when the user queries with guitar or acoustic guitar, you're gonna have a network estimate all these levels of the hierarchy. So is there an acoustic guitar? If no, silence. If there is there any guitar, then you output the mixture of all the guitars in that recording, and then above is all the kind of harmonic instruments, and then the drum is on the other side. And we found that if you train a network to do this, it can actually help it train better with less data at the fine grain level. So it was able. So for example, if you don't have a lot of tracks with acoustic guitar, but you have a lot of tracks with electric guitar, um, the network can leverage that and kind of learns the structure and can improve its performance on acoustic guitars by learning to separate together the other guitars during training.
And do
Um,
you think is that an instance of multitask learning? Is that
so yeah,
part of
I
why
think
that's working?
I think that's some form of multitask learning, yes, but it's in that case, it's a bit more specific in that the tasks are really related to each other. So we actually impose constraint that the output at the upper level should include the output at the lower level. So, for example, if you have electric guitar and acoustic guitar outputs, their parent is we impose, and let's say you do the separation by using a mask. So a mask is what we typically use. I mean, very often used for separation. It's numbers typically between 0 and 1 that we apply. We multiply at each time and frequency, and we set it to 0 if we want to basically turn this part of this time frequency energy off, and we put it to 1 if we want all of it. And so you can apply a mask to shut off the things you don't want and keep the others. So one way to impose a hierarchical constraint is say, well, I have two masks for the electric and the acoustic guitar, and I'm going to impose that their parent mask is at least as large as the max of the two. And so that kind of imposes a hierarchical structure. And this regularization helps the network train a little bit better.
Nice. Any other challenges come to mind or areas that you're excited about?
Let's see. I'm also excited on the audiovisual aspects. So not only sound, but uh, what I mean in my team, what we're really trying to do is to make sense of a complex audiovisual scene. And so using vision with our partners in the computer vision group at MERL, and trying to tie this with sound. So we did some work on trying to use vision as an auxiliary feature to improve sound source separation. In particular, try to model how objects interact with each other to create sound in a scene. Like think of a stick banging on a pot, uh, and so this kind of visual cues can help you separate better. Yeah, I mean, I'm very excited about trying to. Um, I mean, I would say our ultimate goal in my team is what we call total transcription. So it's like if you have a complex acoustic scene, is to completely transcribe what's going on. So if somebody speaks, you transcribe the speech. You may also be interested in their emotion and how they say it. And if there's music, you could separate the music, potentially transcribe it as well. If there's sound events, you could try to detect them, localize them in 3D space as well. So that's kind of that more holistic approach that I'm pretty excited about.
Nice, nice. Well, Jonathan, thanks so much for sharing with us a bit about what you're working on.
Thank you for having me. Thank you so much.